Okay, this video is looking at an introduction to projectile motion, specifically aimed at Year 12 mechanics at the NCA course in New Zealand. So here's a few key ideas about projectile motion. So the first idea is that when an object travels through the air as a projectile, and let's just give a general idea what a projectile looks like. So a projectile is an object that might be released. So it's a ball here, and it's released at an angle. Someone's kicked a ball or thrown a ball, they've released it, they've let go, and basically it will follow a path, a trajectory, a parabolic trajectory. This is a projectile, makes this shape. Now you can only undergo projectile motion if there are no forces acting on the object once it's been released, except for the force of gravity. That's the only force that can be acting on it. So projectile motion can happen when a bullet is released from a gun, or a shell from a cannon, or a ball from a hand, or an arrow from a bow. They can all undergo projectile motion because as soon as you let go of them, you're no longer applying any force to them, and the only force that is acting on them is the force of gravity. Now, if we assume that there's no friction, we can say that the horizontal component, or them going sideways, okay, so if we're going to the right, their horizontal component never reduces. It stays the same size all the time. Okay, so it always has the same horizontal velocity, and we're going to call that v. Now, it's the same at any time. If I took an instant, v is always constant, so I just use v to represent it. So it's obeying Newton's first law. Because horizontally there are no forces speeding it up or slowing it down, then the object will continue in motion at the same speed forever. Okay, and we assume that because we assume there's no friction. Okay, so the second thing about projectile motion is that an object at the same time as traveling horizontally, it is also traveling vertically, up and down. Now it's a wee bit different. The vertical velocity on this ball we could think of as starting up, going upwards. But when it gets to the highest point, what's happened is because of the force of gravity accelerating the ball downwards, it essentially slows the ball down or decelerates it until it gets to the top and it equals 0 meters per second. Just like a straight vertically up and down object. As it goes down, the gravity is still acting on it, accelerating it downwards, so its vertical component gets larger. And when it gets back down to the same height, the vertical component of the velocity should be equal, but opposite to what it originally was. So the vertical velocity is constantly changing because it is constantly being accelerated downwards at negative 9.8 meters per second squared. Just let me make this correction here. Squared. Okay? So the next thing we need to know about projectile motion. If we want to solve these problems, then we're going to have to do the same sort of solving we've done with vertical motion problems or with acceleration in a straight line. Except it becomes quite complicated when we say that it's moving horizontally and vertically at the same time. So we're actually going to split them up into looking at the vertical and looking at the horizontal. So you'll see when we look at the example on my next slide how we're going to do that. Now it's interesting to note also that at any point in time, the overall velocity, so the actual velocity that you would know, the direction it's going and the overall velocity is a combination of both this, our vertical component, and the horizontal component, okay? And this would be the overall velocity at the start. Halfway at the top, at the maximum point, its overall velocity would just be horizontal. Coming down, its overall velocity would be a combination of these two arrows, would be about there, and at the bottom its overall velocity is like that. Now we'll go over that overall velocity concept a bit later, but let's look at a simple example, maybe the most simple example for projectile motion. In this case, we have a runner, parkour runner, let's say, they're jumping off a 10-meter high building. Okay, let's hope they've got a crash pad at the bottom because it's quite a decent height. But they're going to be running along horizontally at 5 meters per second. There is no vertical motion for a start. So initially, the horizontal velocity is 5 meters per second. And I'm going to put a table here, and I'm going to keep my horizontal and my vertical separate. Now let's think about our vertical velocity. If it had no vertical velocity at the start, if this person just ran off horizontal, as soon as they left their supporting ground at the top here, the initial velocity vertically is going to be 0 meters per second. We can see that vertically this person is going to travel 10 meters till they reach the ground. So we can say their height, or what we would call the distance, is equal to 10 meters. And we know from before, when we looked at vertical motion, when we look at this going downwards vertically, it's been accelerated by just one force. That's the force of gravity, and it causes it to accelerate at 9.8 meters per second. Now, here's a question that we've got that they're going to ask us about this. Find the distance the man lands from the cliff's edge. Okay, so this is a bit complicated. They want us to find the distance horizontally. We sometimes call this the range, and sometimes we use the symbol R to represent this. But in our equations, it's always called D. So let's have a look at the horizontal though. If I want to find D, horizontal, I need to know, well, let's have a look at this. I know this equation here, V equals D over T. Remember, if I multiply both sides by T, I can now get this equation. If I want to find the horizontal distance, I times it by the time and by the average velocity. Well, the velocity for horizontal is always average because it stays constant, so it's always at 5 meters per second. So in order to find the distance, I need to find the time. In order to get the time for the horizontal, for the time it was in the air, I can use the vertical to find out what time it's been in the air for. So I actually want to find the vertical time. So I'm going to do that. I'm going to find the vertical time, and then once I know the vertical time, it's the same as the horizontal time. And then from that, I can find my D. So how am I going to do that? I'm going to find an equation that has the 3 things I know and the 1 thing I don't. I don't know T, but I know D, A, and VI. Now let's have a look at this, because now I've found this equation, and this equation is quite useful, but only useful when my initial velocity equals 0. Otherwise, it gets quite difficult to rearrange. Now, the reason that that's useful when it equals 0 is because 0 times t equals 0. And 0 plus anything just equals what it initially is. So I can simplify this equation and just cancel out, or get rid of that whole term. So I get rid of that whole term, and here's my simplified equation. And it has acceleration and distance, and I can find time. But I'm going to have to rearrange it. So the first thing I'm going to have to do is separate these from my time. In order to separate this from time, I'm going to have to do the following. Well, to get rid of the half, basically what I do is I multiply both sides by 2 over 1. Because if I multiply a half by 2 over 1, I get 2 over 2, which is just equal to 1, and it cancels out. To get rid of the a, I divide both sides by a. So I get 1 times a at the bottom. I cancel out the 2 a's. So now what I have is I have 2d divided by a equals t squared. t squared equals 2 times d divided by a. Now, what I want to do is I want to get rid of the squared here. So to get rid of a squared, I square root both sides. That gets rid of the squared here. They cancel out. And now I have t equals the square root of 2d over a. Fantastic. We put the values in. We substitute in the values and we solve. And we get the answer of 1.4 seconds. Okay, so 1.4 seconds. That's cool. Well, this is quite a useful answer here, because what this is telling us is that this person, when they jump off here, will be in the air for 1.4 seconds. So they're going to travel vertically for 1.4 seconds, but they're also going to travel horizontally to 1.4 seconds. For 1.4 seconds. So now I can solve and find the time. I know the time. I can find the range, the distance horizontally. So the distance horizontally is just time times the velocity, because the velocity never changes. So I use this equation, d equals v times t, and I get my answer of 7.1 meters. Again, it's been rounded to two significant figures because my initial data was limited to two significant figures. Interesting to note, and I'm just going to do this as a very quick aside, that at the end of the journey, this person down here will be traveling sideways at 5 meters per second. They are going to be traveling downways. Well, if I wanted to work that out, I would have to work out the final velocity. And I won't do that at the moment, but I'm going to say that they're going to be traveling down at about 7. Okay? 7 meters per second. So when they hit the ground, because they're going horizontally and vertically, their actual combined velocity, their combined final velocity is the hypotenuse of these two sides. Anyway, let's look at the next slide I've got here. And this slide just shows an example of projectile motion here. So the example here is this person is kicked a ball and dropped a ball at the same time. And because both objects, and they're identical balls, let's assume, so they're both accelerating, and it shouldn't matter too much if they're not, actually. They're both accelerating at 9.8 meters per second, downwards. So they will actually go the same distance every second downwards. Even though the one that's been kicked will continue to go horizontally the same velocity each time, as it goes downwards it increases. So the ball that we drop, we can see a path of directly down with the distance vertically increasing all the time, and the one that we've kicked shows this projectile motion path as though it started from the top, because we did start it from the top. They land exactly at the same time. The horizontal velocity that we give something is perpendicular to the vertical velocity, and it has no effect on the vertical velocity. The horizontal velocity has no effect on the vertical velocity. We treat them as different situations. So if we were to say that one was kicked and one was dropped, they're going to hit the ground at the same time. And that's my video on projectile motion. Okay, if you like this, go back and watch the others on vertical motion and the one on motion acceleration in a straight line. And I'll give another couple of examples of vertical motion in the next couple of days.